Once you have identified a suitable location where the catchment water yield is greater than the demand that's required for the new town and to maintain the compensation flows in the river, the next thing you need to do is to work out how much storage is going to be needed in order for a reservoir that's constructed in this location to have only a 1% chance of failure in any given year. Another way of saying this is that this is the storage needed to withstand the 1 in 100 year drought scenario. So how do we do this? Well, we're going to take the synthetic river flow record that you've generated for each of your dam site options, and then you need to do an analysis of the low flow characteristics for each of these. The way we do that, I'm going to illustrate using the data in this table below. So the important thing when you're designing your dam storage is that you need a suitable time step at which to consider the flow volume that's available, and we're going to use a monthly time step here. So as you can see in this data table, I've tabulated data for a number of different years, and I've done that for each of the months. Now the data inside the table is completely made up, so it doesn't really bear any relation to your project. It's purely indicative so that I can illustrate what you need to do. So you begin by looking at what the 1 month minima is in each year. And if we just go down through the table, you'll be able to see that the squares that I'm highlighting are the minimum recorded flow in those calendar years. And so you would take all of those data, you would do a return period analysis on those, and then you would do a regression and extrapolate to find the 1 in 100 year return period flow value. And I'll show you a little bit more how to do that regression analysis in a few moments. But once you've done that for the 1 month data, you would then repeat that for the 2 month data. And so from our indicative table here, I've just highlighted where the 2 month minima would be formed from, and then you would repeat a similar return period and regression analysis. Now the slightly tricky thing here is that you don't necessarily know the crucial period of aggregation in months for which you're going to have to design your dam. And what I mean by that will become evident in a few minutes. But what we need to do is to not only look at the 1 and 2 month minima, but we need to look at the 3, 4, 5, 6, 7, 8, 9 and so on month minima. And as you begin to do that, you start to cross over from one year to the next. And so we need a quick way of doing this analysis to take our flow data and provide ourselves with a data set that we can quickly analyze. And here's an example of how you might go about doing that. So in Excel, I've got some flow data, and once again, it's for the same period as the record that I've provided you from Silmarie, but these data are from somewhere else, so the numbers won't correspond to the ones that you're having to produce. And what we want to do is to create a table that allows us to find the 1 month minima, 2 month minima, 3 month minima, and so on and so forth. So I begin by creating myself a table here, and I'm going to go from 1 to 12 because that's just a nice round number. I'll make my Excel sheet slightly smaller there. And I'm going to take the extent of my data here, and so for the 1 month I'll do this. For the 2 month I'm going to time shift this by 1 month, and again and again and again and again and again and so on and so forth. So I shall shift by 1 month each time. And so what this now means is if I were to insert some columns in here and move that to the side, I can then recreate my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and if I just make this a little smaller in here, In actual fact, my 1 month record is going to be the same as here, so I shall just add that in here. My 2 month record, well, I don't have a value in here, so I'm going to lose a month at the beginning. And so my 2 month value, I'm going to have the sum of those two. My first 3 month value is going to be the sum of those three, and so on and so forth. So I've now completed this procedure for the different months of aggregation, and now that I've done this, I've also brought my labels of year and month over here. If I go to my first value, it will just repeat the formula down here, and so I can easily generate my new time series of rolling totals. And once I've done that, I'm going to paste those values into a new spreadsheet ready for my analysis. So what you now have is a set of time series of the rolling n month total plotted against the final month of that n months. And this is the data that you should use to estimate your return periods at those different scales of aggregation. Now what you will notice is that you progressively lose a month in here, so you might have to discard some of this data up here to make your analyses consistent. And once you've done that, you'll also have to figure out a way of picking out the minimum value in each calendar year on which to base your analyses. Just a couple of things to bear in mind when you're doing the analysis. The original flow data is given to you as a flow rate, and what you're actually interested in for the design of your reservoir is a volume. So you'll need to figure out a way of transferring the data from being expressed as a flow rate to being a flow volume before you start doing this analysis. You're now ready to produce the estimate of the required reservoir storage to meet the design criterion that there must only be a 1% chance that it will fail to provide the volume of water needed in any given year. So to do this, we use a plot like this on the right, where we're going to plot water volume against consecutive months. Now I realise that there are no units on the vertical axis. I've put some numbers there, but that's because this is purely indicative. You will be able to produce a plot that looks like this, but you'll have to figure out what the units are for water volume that you want to use. So when you start off with this plot, what you need to do is to plot what the estimated demand will be over consecutive months. And that's why in the Spark task I asked you to estimate this per day and then also per month, and to articulate what assumptions you would have made when you were doing that. And then we need to compare this with what we think will be the amount of water available in the year when we have the 1 in 100 year drought event. And so this is where you need to analyse the synthetic flow series and the data that you've just been creating, as I showed you in Excel, in order to extrapolate to the 1 in 100 year event. Now you have to extrapolate because the data that you've got is for fewer than 100 years, so you need to do some analyses, do a linear regression, and then extrapolate that out. And the way that you do that is that for each m month set of flow minima, you need to calculate the return period, and that's based on the number of years of data, and it's based on the rank order of minima. So you create a table like that we've got here at the bottom right of the rank order of the minima, and then you calculate from that the return period for each. And then what you do is you plot the runoff minimum against the estimated return period, and you do that on a log-log scale. And so once you've done that for the 1 month values, you do it for the 2 month values, and so on. And this is roughly what you should find. So you get your 1 month line, there are your values. You then do a linear regression on that, and then you project that forwards to the 100-year return period. Now in reality, you'll do this for the 1 month totals, you'll get the linear regression line, and then that will give you the runoff minimum in terms of the return period t. So then what you need to do is, from that equation, substitute t equals 100 and come up with your runoff minimum value. And once you do that, you then take that and transfer it across and plot it on the water volume plot over here. You would then do that for your 2 months, and then 3 months, and 4 months, and so on, until such time as you have built up the availability curve for the 1 in 100 year drought event for all of those different time periods. And I'm going to stop at 11 months. So what you'll see on the plot is that we now have a demand line and we have our availability line, and this is the availability line for the 1 in 100 year drought event, and you'll notice that our availability line is below the estimated demand line. So next what we do is we connect up those dots to make a curve, and what we want to find is the maximum distance between our estimated demand and our availability line. So if I just send a bar up and down there, you'll notice that it gets larger and smaller, and then I can move it back down, and the maximum storage deficit occurs here at just over 6 months. And so that is the storage that you need to provide in your reservoir. And the easy way to find this, if you're doing this analysis, is to simply move that down here and find the point at which your demand line becomes the tangent to your availability curve, project that back, and the intercept on the y-axis, or the water volume axis, will tell you the reservoir storage that is needed. And this is called the active storage, and we'll come on to that a little bit more in the next video.